So today we are going to see the nucleophilicity of NaI, NaBr, NaCl and NaF in different solvents. So let's go. First we will see non-polar solvents. So the mu, which means the dipole moment for the compounds, is 0. For example, the solvent can be CCl4, CS2, etc., like benzene also. Okay, so we have to study characteristics of NaI, NaBr, NaCl and NaF in these solvents. So first of all, you should know that like dissolves like. Okay, like dissolves like. This means that a non-polar solvent will dissolve a non-polar solvent, while a polar solvent will tend to dissolve the polar compounds or polar molecules. So following this fact, we will put out our theory. First of all, look at NaF. When you see NaF, look all the molecules. They are all ionic. Okay, if something is ionic, it means that it possesses some dipole moment. It means these compounds, these molecules are polar, which means that they will not dissolve. They won't dissolve in the non-polar solvents, because we already talked that like solvents dissolve like solvents. Non-polar will dissolve non-polar. Non-polar will not dissolve the polar solvents. So we don't talk about nucleophilicity in these situations where we have non-polar solvents. Now the next one is polar solvents. So in polar solvents we have two types of polar solvents. One is polar protic and one is polar aprotic. So what does polar protic means? Protic means protic gives us an idea about proton in our mind. So it's something related to proton. Proton is what? H plus. So those molecules which contains H plus, like those polar molecules, not H plus, I mean hydrogen atom, OH2, which is nothing but water. Or we can take like HF, HCl, these kind of compounds which are polar and have hydrogen. Now let's talk about polar aprotic. Polar aprotic solvents are like you can take acetone or DMSO, which looks like double bond O, Me and Me. Okay, so these are the basically solvents which we will basically see in organic chemistry. So let me write some polar aprotic solvents which are necessary. Ethers are also polar aprotic solvents. Like if I take an example, this is diethyl. I have ethyl group here. I have ethyl group here. This is diethyl ether. Crown ethers are the cyclic ethers. For example, if I take, this is called THF, tetrahydrofuran. Tetrahydro, these 1, 2, 3, 4 types of molecules you can understand, and furan is for the oxygen. This is the old language of chemistry, old common language. The other is very special, which you will see many times in the organic chemistry. Okay, we will understand the polar aprotic solvents using this one, because this is very widely used. and also acetone is also very widely used in terms of aprotic solvents. So now let's talk about polar protic solvents. So we know that NaI, NaF, NaBr and NaCl, all of these are polar, and we are also taking a polar solvent which is especially polar protic. So surely everything will dissolve. Everything means ions will dissociate. What I mean by ions will dissociate, I mean that NaCl, suppose NaCl is made up of Na plus Cl minus. By dissolution I meant this, that it will deform into Na plus and Cl minus. The lattice of this will break in Na plus and Cl minus. Okay, so now let's understand what will happen. So we have a polar protic solvent. The most common polar protic solvent is H2O. So we know that H2O itself can do hydrogen bonding with another H2O molecules, but we are gonna see the hydrogen bonding with other molecules, like we have Na plus and I minus, Cl minus, Br minus and F minus. Let me draw Br here, Br minus and Cl minus. So tell me that which of them is bigger. Obviously I minus is larger, so it has high electron density, means one electron or one electron charge is present on a smaller molecule, while on a bigger molecule, on a more big molecule, on a very big molecule. Okay, so the charge density is very less. The charge density here is very less. By charge density I mean the charge upon the volume. Okay, here is more, and here is the maximum, here is the minimum, maximum. So what is gonna happen, that H, the structure of H2O, this possesses a del plus, so this will tend to attract with all of these and F minus also. But where will it get most attraction? The best bond, it will get the best bond where it gets high electron density. If he tries to make the bond with I minus, what will happen is the I minus size is very big, so the electron density is spreaded. So so we know that bonding are usually done with overlapping. So if the H plus size is the same, if it overlaps like that small volume comes. If it also overlaps with F minus, the small volume comes. But this small volume and this small volume which contains the more charge, obviously this contains more charge because it has a high electron density. So it's better, it's stronger H bonding here. The H bond will be stronger here and it will be weak here, strong to weak. Okay, so let's understand this. So now what will happen is that all the H2 molecules, like okay, first of all get this clear, that I am checking the nucleophilicity individually, means I am not putting all of them in the same container. No, I am doing this in different containers, one by one. Okay, suppose I keep F minus for a reaction in H2O. What will happen is that a large amount of hydrogen bonding can take place with this because of the high electron density I talked about. So what will happen is many H2 molecules will come and try to bond with it. Okay, but with the Cl minus, what will happen is that not much molecules will come, smaller layers of the solution will be formed. What are these? These are the H2 molecules surrounding the ion. They are doing H bonding with the Cl minus ion. The hydrogen atoms are doing the H bonding. While if I see Br minus, then very small layer, and with I minus, negligible, very negligible, very negligible H bonding will take place. So we can see that F minus will be least available. Its electron are already distributed between the H bonds, while I minus is very free in the solution. Okay, so if I minus is very free in the solution, and most free is I minus, then Br minus, then Cl minus, and the least free is F minus. So what will happen? The more concentration, the more the amount of nucleophile is present, not basically the amount, not I am not talking about the amount, but I am qualitatively checking their availabilities. Like I minus, these electrons will be highly available, while these will not be much available, and these will much more not available, and this will not available. So the nucleophilicity order will be like that, simple. This will not be able to donate electrons, this will be able to donate electrons, but very few. This will also be, but very few. My bad. This will not be able to donate electron, but it will donate some more electrons, and it will donate some more electrons than Cl minus, and it will donate some more electrons than Br minus. And nucleophilicity is nothing but the game of electrons. The more electrons something have, the more tendency of electron giving something have, the more nucleophilicity. So I hope this is clear. So let's kind of stop here and ask ourselves a question. If nothing condition was given, if no solvent was told to us that what solvent we are performing the reaction, you did not know about that solvent. The solvent also depends upon the nucleophilicity also depends on the kind of solvent we are using. What would be your answer to the nucleophilicity order for F minus, Cl minus, Br minus, I minus? So when I am talking about F minus, Cl minus, Br minus, I minus, I am saying that they are available in solution. I mean that NaI, which is ionic, has broken down into Na plus I minus, and this I minus has come from this Ni. Okay, I am talking about that. So you would have thought that okay, see, F minus has a larger electron density and Cl minus has lesser, and while it has a least electron density. So I would prefer that as the size is increasing, the electron density is decreasing. So F minus, now remember the fact that when we talk about a period, we talk in terms of electronegativity, but when we talk in groups like halogens, group 17 elements, we will talk about the sizes. So the it has a very large size, so we told that okay, this has a very large size, so its electron density will be very low. So its electron will not be as much efficient, or overlapping with this will not be much efficient than the F minus. Okay, so this is nothing but the order for polar aprotic solvent. Now let me tell you the reason for this. So I have chosen PAS, polar solvent. So NaI, NaF, NaBr, and all of them will break, and I I minus, F minus, Br minus, Cl minus will be available in the solution. So now we have to see the solvation effects, means that how much the bonding type of stuff will be going on. Like if I see F minus, so can it interact with the minus charge? No, it will tend to interact with the plus charge. But will this interaction be very effective? The answer is no. The del plus is the charge on this carbon due to the electronegativity difference of carbon and oxygen. And also the factor that will dominate here is these CH3 groups. These groups will repel this anion from coming closer. So in polar aprotic solvents we neglect these effects, del plus and the minus. Which effects exist, this is also very important to talk about. So what makes PAS different from PPS is that PAS will not do anything with anion, but with cation it does the same thing as the PPS does with the cation. So I have not shown you what a PPS does with the cation. Now I will show you what a PS or PPS do with cation. So we can easily see that this del minus cannot interact with the anion, but it can surely solvate this cation. They can solvate the cation, and basically it's of no use for us basically, but yeah, you should have just some kind of information. So now what we will do is that we will compare the nucleophilicities. Okay, I can remove the Na because this will exist as free ions. Br minus, Cl minus, F minus. So what's going to happen? I will see that now there is no solvation, unlike that of PPS. PPS it was solvated. So I told you that F minus has a larger electron density and all of that stuff that we have talked about. You can easily tell that this will be the nucleophilicity order. So I hope you enjoyed.